Hi folks, we're going to take a look at number 15 from page 429. So I've already drawn a diagram here, so let's see what the question asks. It says that a box in the shape of a square-based prism. Okay, so you notice here that the base has equal sides, and the height of the box is twice the width of the base. So that's why the height here is just 2 times whatever I chose to call my base, which was W. And in part A, it wants us to show that the longest thin rod that can be encased in the box has a length of root 6 W. All right, so let's start by adding something to our diagram, which is how we would place the longest thin rod. So it makes sense that the longest thin rod would go along the diagonal from one corner all the way to the opposite corner. So let me just draw that here. So this would be the longest rod I could put in, and we want to find an expression for that length. So not surprisingly, you know, the answer that they're telling us we should come up with has a variable in it, since we don't have any specific information about this box other than its general shape. All right, so let's call this L. So that's what we're looking for. Now this is a problem you've solved before. In fact, I think we've solved it in this course previously, and probably solved it also in grade 9, is to use Pythagoras here. So what we know are the lengths of the edges, or at least we have expressions for the lengths of the edges, and we see this length of rod as being part of a right angle triangle. It's a right angle triangle with this side. We can take this edge, this longer edge here, and use the blue one again. We can use the diagonal of the square at the bottom. And this here is going to be a right angle triangle, because obviously the base, since it's a rectangular prism, the base is perpendicular to the height. All right, so the first thing we're going to do is find this length here. Okay, but this, of course, because the length and width are also 90 degrees, we have a right angle triangle there. So to find x, we just use Pythagoras, so we have that x squared is equal to w squared plus w squared. Okay, so that means x is going to be equal to the square root of, well, w squared plus w squared is 2w squared. Okay, and now we can use the fact that this edge has the same length as that one there, so it's 2w, and now use Pythagoras on this bigger triangle to find L. All right, so since this is hypotenuse of that triangle, we have that L squared is equal to this length squared, so the square root of 2w squared all squared, plus this length squared, so 2w squared. So notice how it's important that I use brackets here to make sure that I'm squaring the whole side. All right, so first of all, this here is when I square a square root, these are opposite operations to each other, so they annihilate each other. So here I'm just left with 2w squared, plus here when I square a product, I can just distribute the square to both of those expressions. Okay, so 2 squared is 4, and w squared, just w squared, and here, oh, lo and behold, we just have 6w squared, so that means L is just going to be equal to square root of 6w squared. Okay, now this is where we're going to have to use some algebra, because they actually tell us to show that this is equal to root 6 of w. So the question is, are these two things equal? I think if you look at them, it looks reasonable that they would be equal, but this is actually a property that you won't be seeing till the next course that allows you to split up the square root of a product into the individual square roots, because this looks a lot like just the square root of 6 and the square root of w squared. And we're not going to go and prove this here, but what we're going to do is I'm going to square this thing. We know that if we square this, we get 6w squared. I'm going to see if we get the same thing when we square root 6w. Okay, so in other words, we write root 6w times root 6w. If it gives us the same result, then it justifies that these two things are indeed equal. And let's see what happens. So here we're multiplying these two expressions, and we know that multiplication can be done in any order. So I could choose to multiply these two things first, so root 6 squared, and then I can multiply these two W squared, and of course root 6 all squared is just going to be 6W squared, the same as we had originally. Okay, so we'll use this as a justification that's the same as root 6 times W. Okay, but in grade 11 you'll actually prove that that's indeed correct. All right, so we've done part A. Now what part B asks us to do is to find the angles at which the rod would make with the edge of each box. All right. So while there's lots of edges here, I'm only going to deal with the one long edge, and then these two are essentially the same. So I'm just going to calculate two of these angles here. All right. And one of them we can work with pretty easily because it's already inside the triangle that we have. We see that this angle here, okay, which I'll call theta, is the angle to the longer edge, okay, and it's part of a right angle triangle. So that's what I'm going to use to determine that. Angle. All right. So let's see what we have. We have a couple of sides here. Okay. In fact, we have all three sides, so we can use any two, but I'll use this 2W, okay, which is adjacent to theta, and I'll use L, which I just found, which is the hypotenuse. So adjacent and hypotenuse, I'm going to use cosine. So if I take cosine of theta, I get adjacent, which is 2W, divided by hypotenuse, which you just found was root 6W. And hey, look what happens. W divided by W is equal to 1. So I just have that theta is going to be cos inverse of 2 over root 6. All right, which is something we can calculate pretty easily here. So cos inverse of 2 divided by square root of 6 is equal to 35.3. Okay, so 35.3 degrees. So I would say that's the easier one, okay, because we already had that angle inside this triangle. Now let's take a look at how I can find the angle to, say, this side here. Okay, so I'm looking for this angle, okay, which I'll call phi. But this angle here, well, what I'm going to do is I'm going to create a different right angle triangle. All right, I'm going to create a right angle triangle between, which is just the diagonal of this side of the shape, the W here, and then the length of the rod. Okay, and this is again a right angle triangle. Why is it a right angle triangle? Well, because this face of the shape has to be perpendicular to that side length. All right, and I don't even have to find this length here because I only need two sides to find the angle in a right angle triangle. All right, so if I want to find that, I see that W is again adjacent to phi, and L is the hypotenuse of this triangle, so I can again use cosine. So cosine of phi is equal to the adjacent side, which is W, over the hypotenuse, which is L, which is root 6 times W. And look what happens yet again. The W's reduce, so that means phi is just equal to cos inverse of 1 over root 6. All right, and let's get an answer for that. So here, cos inverse of 1 divided by square root of 6 is equal to 65.9. All right, so here 65.9 degrees. Okay, and there we have it. We've solved the problem. So this one here, a bit of a toughie, but let's go back to step 1. Step 1 was to get ourselves a good diagram. All right, step 2 was to realize that we were going to be working with the diagonal of this box, okay, and then to follow the pattern that we'd used in the past to find the length of the diagonal, which is to create this right angle triangle, except here we had to keep the variable along the way. All right, then once we found an expression for this length, we were able to use these two right angle triangles to determine the angles to the edges, okay, the long edge and the short edge of this rectangular prism. Okay, that's it for this one.